Welcome to the viewers for the lecture in the subject structural analysis. This is lecture number 161, in which we are going to discuss about the analysis of building frames subjected to lateral loads. The lateral load in a structure may be due to wind force or may be due to seismic force. So when a structure is subjected to lateral loads, how to analyze and how to find out the bending moment, etc. We'll discuss. And we are going to discuss the analysis. Actually, there are three methods. One is portal method. Second one is the cantilever method. And the third one is the factor method. Right. And we are going to discuss the problem with the simplifications and also some shortcuts. Actually, when you look at the calculations in any book, you will find the problem is complicated, involving a lot of calculations, a lot of figures, etc. It is not at all. First of all, I simplify the problem. Right. Now, the structure may be statically indeterminate. When you consider a multi-storied, multi-bay frame, we know it is statically indeterminate to number of degrees. Of course, we can find out. So first one is that of making the structure statically determinate. That will hardly take 2 minutes, right? So converting the structure as a determinate structure using some assumptions, right? Next one is we have to find out the horizontal shears at the mid heights of stories. Horizontal shears at the mid heights of stories. So these two steps will make the structure completely determinate. Once if the structure is determinate, with one or two steps of calculation for the horizontal shears, the rest of the problem can be completed without any calculation. Simple calculations will be able to do it in a very short period. That is what I told you, shortcut. I'll explain. But however, shortcuts can be used by practical designers for simplifying the calculation work. But for students, from examination point of view, you have to show the calculations. Those calculations again will be simple only, because after making the structure statically determinate, we are going to analyze the structure only by using the equations of equilibrium, sigma v equals 0, sigma h equals 0, and sigma m equal to 0, right? And then we have to draw the bending moment diagram, right? Let us discuss the problem through a numerical example. Using the portal method, analyze the building frame subjected to horizontal forces as shown in figure. Sketch the bending moment diagram or bending moment diagrams. Bending moment diagram means for the complete frame. Bending moment diagrams means for individual members will be drawing the bending moment diagram. But matter is same, right? So this is the building frame, 4 meters, 6 meters, 2 bays, 2 stories, 5 meters and 3.5 meters. Right. Now, before going to the solution, we know this is a 2-bay, 2-storied frame. So it is statically indeterminate to 12 degrees. Number of closed loops into 3 minus number of releases. There are 4 closed loops into 3. 4 into 3, 12 minus all these are fixed. Therefore, there is no release. So 12 minus 0 equal to 12. Therefore, the structure is statically indeterminate to 12 degrees. Now, what we do here is, for making the structure statically determinate, we introduce hinges at the mid-span of beams and mid-heights of columns. That is one of the assumptions, right? So, when you assume hinges, GH, you have got a hinge at the mid-span of GH. At the mid-span of HI, you have a hinge. At the mid-height of column GD, we will assume a hinge. Mid-height of column HE, we will assume a hinge. Like this, we can assume 10 hinges, because 2 plus 2, 4 beams and 6 column members, GD, DA and so on. So you will be introducing 10 hinges. The 10 hinges, that is, we assume points of contraflexure at the mid points of beams and mid heights of columns. That is the meaning of hinge, right? Now, once if we introduce 10 hinges, the 12 degrees indeterminate structure will become 10 degrees. And we are going to make one shear equation assumption. So we assume we will find out the shear at the mid heights of columns, at mid heights of top story columns and the bottom story columns. So these two will be the additional equation which will make the structure statically determinate. Right. And with this introduction, these are the assumptions. Points of contraflexure. That is assuming the hinges at the mid points of beams and columns. Second assumption, this is another important assumption. Frames having several bays are assumed to be behaving as a series of single bay portal frames. The meaning is, suppose if you have this frame, the panel A, D, G, H, E, B will be one frame. This is the next frame, namely B, E, H, I, F, E, I, F, C is another frame. So this will behave as two frames placed side by side. That means this column HEB is common for both the panels, both the portals. Portal 1, this is portal 2. This column is common. Therefore, the second assumption is the horizontal shear taken by the interior column or interior columns will be twice that of the horizontal shear taken by the exterior columns. That is the second assumption. This is the second assumption. You can stop and read later. Right. Now, this is about the hinges, the assumed hinges O1, O2, O3 and so on. As I told, there are 10 hinges up to O1, O9, O10. There are 10 hinges. Right. This is assumption. Right. The shears. That is, we are calculating the shear at the levels O1, O2, O3 and O4, O5, O6. So at the middle of the top story, namely at O1, O2, O3, above this, you got only one horizontal force, 60 kilonewton. This is the free body diagram. So let us assume the shear as S1. So here, twice S1. Interior column will take 2 times the shear because this column is common to portal 1 and portal 2. Right. So this is S1. Now, S1 plus 2S1 plus S1 minus 60, this force equal to 0. That will give you the value of S1 equal to 15 kilonewton. This is sigma H equal to 0. That's all. S1 equal to 15 kilonewton. This is one equation. This is the 11th equation, you can say. Right. The 12th equation is assume the hinges at the midpoints of the bottom story O4, O5 and O6. Right. Now find out the horizontal shear at this level. At this level, let us assume this as S2. We know it is 2S2. This is S2. So S2 plus 2S2 plus S2. There are two forces. One is 60. The other one is, there are two forces above the level of the hinge. So 60 plus 40. So you can understand this. 4S2 equal to 100. Therefore, S2 equal to 25 kilonewton. So we have calculated shears at two levels. One is S1. The other one is S2. So 10 hinges plus S1 plus S2 has made the structure as completely determinate. After this, we have to find out the moments at various points and draw the bending moment diagram. Now first we will mark the columns and then we will calculate the bending moments at the ends of members. Here we are going to just make use of sigma H equals 0 and sigma M equals 0. Suppose if we take the top panel from G to O1, the mid height O1. G to O1, it is 1.75 meters because the top panel is of 3.5 meters, right? Half the value is 1.75, right? Now this value we have calculated 15. So when this is 15, for horizontal equilibrium of this element, this also has to be 15, the horizontal shear. But these two horizontal shears will cause a clockwise moment of 15 into 1.75. 15 into 1.75 is 26.25. So actually these two forces will cause a clockwise moment of 26.25. For equilibrium of this body, there must be an anti-clockwise moment of 26.25. So now this free body is under equilibrium. Second one, we know the shear at this level is 30, 2 times S1, 30, same 1.75. So this is for making sigma h equals 0. So these two will cause a clockwise moment of 30 into 1.75. For equilibrium of this element, so there is an anti-clockwise moment of 30 into, that is equal to 52.5. Same thing here. Same thing here. Same procedure. Here it is, this is the second part of the top story. This is up to the mid height. This is below the mid height. So same value, same procedure, same calculation. Will not repeat, right? Now coming to the bottom story, we know S2 equal to 25. 25. So 25 into 1.25 as discussed above. 25 here also it will be 25, the horizontal force 25. 25 into 2.5 is 62.5. So this will cause a clockwise moment. So therefore for equilibrium there must be an anti-clockwise moment of 62.5. 62. Right. Similarly, this is 50 into 2.5 because bottom story is of 5 meters height. So all other calculations you can understand. I'll avoid further discussion because same procedure. I'll just repeat through. The viewers can stop at any stage and you can just leisurely go through. You can easily understand. Right. Now, this is about the column moments. Now, coming to beams, we love beam GH, HI, etc. For calculating the bending moments in the beams, there is a procedure, step-by-step procedure. But first, let us discuss the shortcut. Without even those calculations, you can straight away draw the diagram. This will be more useful for the practical designers and also to check your values. Whether you are doing the calculations right or not, you can easily check. So for that, it will be helpful. So first we will discuss the shortcut and come back to the calculation. These are the calculations we will discuss little later. Right. Now coming to this, same. Now this is beam GH. We know that at this joint G, when there is an anti-clockwise moment of 26.25, for equilibrium of this joint, 26.25 must be clockwise. So these two will make sigma m equals 0 at the point G. Similarly here, when this is anti-clockwise 26.25, this is clockwise 26.25 to make sigma m equals 0 at the point I. Right. Here you may have a doubt because if you consider GH, in GH there is no external force, and here you must have a hinge. We have assumed hinges at the midpoints of the members. So when this is clockwise 26.25, in the absence of any other load or any other moment, this also has to be clockwise only because at this point there will be a point of contraflexure. So the diagram will be a straight line. The bending moment diagram will be a straight line. So here there will be a point of contraflexure. So when this is 26.25, this also will be 26.25. How this is 26.25? You are going to calculate and discuss. This is only shortcut, right? 26.2. Similarly, when this is 26.25, this is also 26.25. The check that is available at this point is plus 26.25. This is plus 26.25. Here it is minus 52.5. This already we have calculated in the columns. The sum of these must be equal to 0. You can always check. Right. And other calculations that the viewers can understand. because this already we know, this already you know. So when this is anti-clockwise 26.25, when this is anti-clockwise 62.5, this must be clockwise. Coming to the numerical value, 26.25 is anti-clockwise, 62.25 is anti-clockwise. Add them, the sum will be the clockwise moment here for to make sigma m equals 0 at the joint G. All the three values will have to be added. Right. Now coming to this also, it will be same calculation. And when this is 88.75, this is 88.75. Similarly here, this value is already known. This value is already known. That is 30 into 2.5. Sorry, here it is 50. The shear is 50. 50 into 2.5. This is known. This is known. These two we have written now. So the sum of all these things, clockwise, anti-clockwise numbers, when you add, the sum will be equal to 0. So with this, the red marks, these are to indicate the direction on which tension occurs, or the direction in which you have to plot the bending moment diagram. You have done number of problems, same procedure, right? So with this calculations, you will be able to straight away draw the bending moment diagram. On the tension side, you will have to plot the bending moment, no load, no other moment, therefore straight away it is a straight line. This is the bending. So this is bending moment diagrams, because for individual members we have drawn the bending moment diagram. You can combine everything and you can draw a simple bending moment diagram. Single bending moment diagram can also be. This is the bending moment. So that completes actually this shortcut. Now we have to discuss, however, because in the examination you have to show the calculations. That is, what we do is, you have to take individual panels. That is, in the frame, in the frame, let us take this part. O1, this is G. O1G, O7 is considered as a free body diagram. Free body diagrams bounded by the hinges. And the next free body diagram will be O7, O8, O2, bounded by the three hinges. The third free body is O8, I, and O3. That is the third free body. Similarly, here O1, O4, O9. Then O9, O2, O10, and O5. This is one free body. Like this, you'll have to consider the structure as number of free body diagrams. So that is what we are going to consider here. Now, the free bodies bounded by hinges are considered. Free bodies bounded by hinges are considered. Just now we have discussed. Then, axial forces will be there in all members. Axial forces both in the columns as well as beams. Now, what we are going to do is, suppose if we take this joint, we are going to find out the moment about the point G. We are going to take moment about the point G. So, the axial force in the member O1G, the axial force in the member O7G will not cause any moment. Therefore, the axial forces are not marked, and also the axial forces are not going to be considered for the calculations. Therefore, even though axial forces are there, they are not marked for the reason that they will not cause any moment at the point G. So only lateral forces are marked. Now in this, we know the value of S1 that we have calculated already is 15 kilonewton. So there will be another vertical force here that we have to calculate. For which, what we are going to do is, we are going to take moment about the point G. That is 15 into 1.75 minus V1 into 2, because first panel is of 4 meters span, therefore half the value is 2 meters, V1 into 2. So 15 into 1.75 minus V1 into 2 equal to 0, therefore V1 equal to 13.125. Right. Coming to this element, suppose if you consider the element GO7, V1 is 13.125. So for equilibrium, there will be another force here, downwards 13.125. This V1 upwards, this V1 downwards will cause an anti-clockwise moment. Therefore, for equilibrium at the point G, the moment will have to be clockwise. So the value MgO7 is 26.25 in the clockwise direction. So that is one value. That is what we have already taken. If this is 26.25 in the left, this is 26.25 towards right. It must be the value, but you have to show the calculations. Therefore, this is the calculation. I will discuss one more calculations and skip the rest of the calculation. So let us take the next free body bounded by O7, O8 and O2. In O2, you have got a shear force of 30, that is interior hinge, twice the value in the outer columns, 30. This is 13.125. How? Here, when this is V1 13.125 up, just to the right of the hinge, it is V1 downwards, because at the hinge there is no other force. So V1 upwards, V1 downwards will make sigma V equal to 0. Therefore, this has to be downwards. Right? So this is known. Now let us find out the value of V2. Take moment about the point H. So 30 into 1.75 minus 13.125 into 2 minus V2 into 3. Taking moment about H. This is the value. These are the calculations. You can always understand. So this will give you V2 equal to 8. V2. Actually, I think I written by mistake. It is not V3. It is only V2. So please correct this. It is V2. V2 is 8.7. V2 is 8.75. So when you find out the moment about this point, V2 into 3 is the value. Namely, the moment is equal to HO8. HO8 equal to V3 into 13.125. 8.75 into 3. 8.7 equal to 26.25. So 26.25 clockwise. Earlier we assumed it to be clockwise. Now we have proved it to be 2.75. So 8.75 down for equilibrium. These two will cause an anti-clockwise moment. Therefore, at the support, this moment has to be clockwise, whose value equal to 26.25. So this is for checking at a joint. The sum of all the three moments must be equal to 0. How you find out the value of MIH? So I think hereafter if I discuss, it will be boring. The viewers can stop at any stage and they can learn. So this is to just show the calculations and prove that the moments and the respective joints. So this is how we'll have to show the calculations. So this is straight away we have discussed a shortcut, and also how to calculate all the values are. So simply we use sigma V equals 0, H equals 0 and sigma M equal to 0. We have considered number of free bodies. That problem is not at all simple. So therefore the viewers are expected to understand the procedure, make the structure statically determinate. One is by hinges, the other one is by the shear equation. Once that is done, the rest of the problem is only the use of equilibrium equations for finding out the moments at various points, and then straight away draw the bending moment diagram. So that completes. So this can be done for any number of bays and any number of columns, because always you will not be discussing 2 bay 2 story, maybe 3 bay 3 story, even 10 stories, no problem. This is the procedure. So that is about the portal method. So thank you. Thank the viewers for their patient listening. Thank you.